Earlier, we had learned to differentiate certain functions like polynomial functions and trigonometric functions. In this section, we will understand the concepts of continuity and differentiability. Let us start with the concept of continuity by understanding continuity at a point. Consider a function f of x defined as f of x equal to 2, when x is greater than or equal to 0 and -1 when x is less than 0. Let's represent this on the Cartesian plane. If we look at the graph and consider the points to the left of 0, such as -0.1, -0.01 and -0.001, the value of the function at all these points is -1. And similarly, for the points to the right of 0, such as 0.1, 0.01 and 0.001, the value of the function is 2 for all 3 points. So, we can say the function value is -1 as x approaches 0 from the left and 2 as x approaches 0 from the right. So, the left-hand limit is -1 and the right-hand limit is 2 at point x equals 0. From this, we can say that the left-hand limit and right-hand limit do not coincide. Note that to draw the graph of this function, we need to lift the pen from the surface at x equals 0. And this is the first instance of a function being discontinuous at x equals 0. Conclusively, we may say that a function is continuous at a fixed point if we can draw the graph of the function around that point without lifting the pen from the plane of the paper. Mathematically, we can define the continuity at a point as follows. Suppose f is a real function on a subset of the real numbers, and let c be a point in the domain of f. Then f is continuous at c if limit x tends to c. F of x is equal to f of c. More elaborately, if the left-hand limit, right-hand limit, and value of a function at x equals c exist and are equal to each other, then f is said to be continuous at x equals c. Let's solve a few problems to strengthen the concept. Example 1. Examine whether the function f given by f of x equal to x squared is continuous at x equals 0. Let us use the definition of continuity at this point. Now limit x tends to 0, f of x equals limit x tends to 0, x squared, which further equals 0. Thus, limit x tends to 0, f of x equals f of 0. Hence, f is continuous at x equals 0. Example 2. Discuss the continuity of the function f given by f of x equals modulus of x at x equals 0. Now we know the definition of the modulus function as f of x equals -x for x less than 0 and x for x greater than or equal to 0. So, the function is defined for all real values. Let's check the continuity at x equals 0. The left-hand and right-hand limits of modulus x are shown. Thus, the left-hand limit, the right-hand limit, and the value of the function coincide at x equals 0. Hence, f is continuous at x equals 0. Let's summarize what we have learned.